Here we go. All right. So next bit. Is there a way to open this in a separate tab? Is she really doing me dirty like this? Hang on. Let me try to pull it up. There we go. All right. What are the steps to create a transgenic organism? What? Motherfucker. You fucking serious? Hang on. I'm gonna fill this in. Recorded. Not even gonna change the color of my text like I usually do. How do you create a transgenic organism? You construct DNA and inject it. Oh wait, and then you inject it into an organism. Yeah, there I can stop, right? You construct DNA, you inject it, and then it becomes transgenic. Then you mate it with a killer. There you go. As a bioengineer, how can you insert a human gene into a bacteria? Why must you go through extra steps? God damn it, I wish he went over this. I'll skip that one. How do I hate this class. I fucking she clearly wrote this at the last minute. Okay, you know what? Let's go back. As a bioengineer, how can you insert a human gene into a bacteria? Why must you go through extra steps? So how do you insert a human gene into a bacteria? Pretty simple. You transcribe it first. Now, you transcribe it into RNA first because, well, bacteria don't have DNA, right? They have RNA, one big chain of RNA. And in order to make sure that you can actually get it into the bacteria without it like dying or immediately rejecting the DNA, you have to transcribe it into RNA because that's something that it can read. Then you use the DNA. Ugh. I'm losing it, man. I'm losing it. I can't even type anymore. Oh, whoops. There you go. Right. So you would use, sorry, I put DNA. It should be RNA here. Right. So first you transcribe it into RNA, then you take that chain, modify it around so that it can be properly read as a construct DNA, and then throw it into a bacteria. How do gel? Man, I'll be thinking about that during the test. How does gel electrophoresis work? An electric is run or ran? Run. Ah, you can hear my suffering. Run through a gel. And isolate specific alleles into separate parts. Now I'll put this into the Discord server, but I'm just going to keep running through this. True or false? In gel electrophoresis, negative charge of phosphate groups is responsible for the migration of DNA fragments. Yes. Ah, freaking. I'm losing it. I am losing it, guys. I'm sorry. Use the paternity test electrophoresis gel to the right to determine if who is the real father. What? All right. Let's determine who the father is. Um, that's one match. You're just basically just lining everything up and matching as much as you can. Mother has this one. Hold on. So this one has one. This one has one, two, three, about four. Oh, four matching. So we'll call it dad two. Oh, whoops. There you go. What are the steps to PCR? Step one. Come on. What the heck? There we go. Step one. What are the steps to PCR? First you step two, you to there you go. That's it. 3 steps to PCR. What ingredients do you need to run a PCR? The machine, the original DNA sample, uh what else? Uh bacterial polymerase and nucleotides. We're gonna skip that. Y'all can do that on your own. I'm kidding. Let's go. Reverse transcriptase. Uh, reverse transcriptase. Hang on. Uh-oh. Uh-oh. Crap, this is all the notes. All right. Google. Here we go. Enzyme used to generate complementary DNA. That makes sense. Recombinant DNA. Jeez, I wish. Artificial DNA. A retrovirus. Ah. Copies of its DNA. Cloning. A transgenic organism. An organism with inserted DNA. Transformation. When foreign DNA in a PCR. Oh, gel electrophoresis. C above. Yeah, I got it. DNA segment below is 41 bases. This example, the flanking sequences consist of 9 bases. The 8 4-base repeat units Gata. Here we go. That's where it stops. Make up the remaining 32 bases. How long would you expect an allele if it had 10 repeat units? So to do this question, which I'm sure some of you don't know how to, right? The ends consist of 9 bases. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, we got the 9 bases on the end. Now, inside there are 8 4-base repeat units, right? That's 1 unit, 2 units, 3 units, 4 units, 5 units, 6 units, 7 units, 8 units. It's asking if instead of 8, we had 10, how long do you expect this to be? Each unit, as we can see here, is worth 4. If I have 8 units already and I want 10, how many units am I adding? 2. If each unit is worth 4, I'm adding 8 bases. So instead of 41 bases, it's going to be 49. Does that make sense? This was a question on the lab if you didn't know how to do it. Yeah, got that. I know I spoke really fast on that one. Did y'all get it? Guys, please. No? Okay. So when you look at this question, it's going to tell you which ones are on the ends, right? 9 bases are the flanking. The flanking is the ones on the end. And then it'll tell you the 4-base repeat units, right? It means this sequence is going to be repeated for each unit. So what do? I read left to right, and I start looking for these repeats. Aha, here's the first one. So let me highlight this actually. So that's 1 repeat unit. Here's another repeat unit. Oh, whoa. Here's another repeat unit. Here's another repeat unit. Here's another repeat unit. Oh, I changed the text color on that one. That's fine. Here's another repeat unit. Here's another repeat unit. And then here's the last one. Do that color. All right. You see, now I've isolated. Oh, come on. I changed the text color again. Hang on. There we go. So as you see, I've isolated 1, 2, 3, 4, 5, 6, 7, 8 repeat units. That means they have the GATA pattern. Now, I know this is 41 bases, so I don't need to count. This is 41 bases wide, right? What it's asking is how long would it be? Meaning, how many bases long is it? Now, I know there's 41. I know that 1 unit is a GATA pattern. This is a unit, this is a unit, this is a unit. It's asking how long would this be if I had 10 repeat units? Right now, I have 8. In order to get from 8 units to 10 units, I have to add 2 units, meaning another 2 GATA pattern, right? And since it's just asking if I put 10 repeat units, I don't need to change any of the ones on the ends, meaning they all just stay there, right? I'm just adding 2 to the middle or somewhere. So when I add 2 of them, right, I'm adding 2 units. Each unit is 4 bases. So how many bases am I adding? 8, right? If somebody decided not to do math today, I'm adding 8 bases. Why? Because it's 2 units and each unit is worth 4. And since I add 8 units, And I already know that this one's 41. If I'm just adding 8 bases, I just do 41 plus 8 and I get 49. Meaning I know this one's going to be 49 bases long. Now, what happens if I take one of the 4 base repeat units out? It will only be, what is it? Rather than being 41, here I subtract 4 because I took out a unit. So it'd be 37. Now, why is this important? And it's also the answer to the second half. How long will the DNA fragment run now compared to the 8 repeat? This is a BP. It's how large the thing is. This one, if it's bigger or smaller, or if it's bigger, it's going to run slower. If it's, sorry, if it's bigger on like how many bases long it is, it's going to run slower. So this one, since the new one for 10 units is going to be 49 bases long, it's not going to go as far as the one that's 37 bases long. So here, it would actually go further. Now, on the gel on the right, which one has the longest DNA fragment? Remember, bigger is closer to the beginning. So it would be A. Sample A has the longest because it's the closest to the start. Whoops. Which sample has the shortest? Look at sample C. It went the furthest. It has the shortest. Identify each band/allele. In sample C, you would just check their lengths. So what is it? We'll just mark them by number going. So there's a 600 BP. There's a, that looks like 300. And then there's a 100. Using a gel, how can you tell if it's homozygous or heterozygous? If the gene has 2 bars, it is there's 1 bar. It's formulas. For homozygous, you're looking at, let me check my labs again. Man, they're really doing us dirty. Where is it? Sorry, hang on. The formulas are in here. I need to scroll up. Here we go. Allele frequency to the power 2. Then here it's 2 times the allele frequency times the how do you determine the probability that another individual has the same genotype? Okay, this is all the math questions. Sorry. Hang on. I'm going to explain this one in a second. Multiply all the. hold on. Write them down on a sticky note and put it behind your laptop. If you need to remember these equations. All right, to do the math. Yes, same, Katie. Bruh. To do the math, what you need to do is look at this big table, right? They're gonna give you two alleles, right? Here it's homozygous, here it's homozygous, here it's heterozygous. How do I know the numbers are different, right? That's pretty simple. Now, to do the math, what you need to do is go through, count how many elephants here share the same alleles, right? Like I'll try to simplify this, but basically you're gonna count how many 193s are here. That'll give you the numbers of allele number 1 that match with your organism in question. Then you count the total number. Here for our lab, it was 20. You divide the two, you get frequency. Frequency, part over whole. It's just a fraction, guys. I swear it's not that difficult. It's just a fraction. You don't even need to turn it into a percentage. Now, what happens next is you do that again for allele number 2, allele number 3, allele number 4, and allele number 5. Those will give you all frequencies. Same thing on allele number 2. It's the allele number 1 is the one on the top, allele number 2 is the one on the bottom, right? So what do I do with once I get all these frequencies? Well, I have to calculate the probability of that allele in a specific locus. Locus meaning the up and down columns, right? FH19, FH60, FH67. Those are all genes, right? The locus is just the genes. So to calculate the probability of having a specific gene in a locus, what you need to do is take the frequency of an allele. If it's homozygous, you square it. If it's heterozygous, you do 2 times the frequency of allele 1 times the frequency of allele 2. Let's give an example. And if you're watching this on YouTube, slow it down if you need to. So here, it's homozygous, right? Why? Look at it, 193 on top, 193 on bottom. They're the same. Since they're the same, I can take this, plug it into my probability, or plug it into my frequency system, right? 12 over 20, 12 over 20, that's 0.6%. I take 0.6%, since there's 2 of them, I just square them. Boom, calculated probability for the locus, 0.36. Same thing here, because it's homozygous, I got 0.80 for frequency of this allele. I square it, 0.64. Now for heterozygous ones, you do 2 times the frequency of allele 1 times the frequency of allele 2. How did I find the frequencies? I just counted how many of the how many 97s there were, and then I counted how many 103s there were. 2 times frequency of allele 1 times frequency of allele 2 gives me the probability. Same thing I did here. Now, once I have probability, what I'm going to do is, how do I determine the chances that something is going to have the exact same DNA as the organism in question? Hint, hint, it's going to be very, very low. Normally less than 1% if you converted it from a decimal into a percentage. How do I find that? I take this number, this number, this number, this number, and this number, multiply them all together, and I get this very tiny number. Got it? I take all the probabilities for the loci, as I've written here, and you multiply them all together. Now, some of you didn't do this table because it was a pain in the butt, but they gave you all the frequencies. So what me and Joseph did was we ran through, calculated all, or plugged them all each into their formulas, got the probability for each locus, multiplied them all together, and got 6.41 times 10 to the negative 17. Now, if you got a different answer, good job. You probably did it better than we did. But to increase accuracy, as number 16 is asking, use more loci. That's it. You analyze more genes. This number, while it's very, very small, and by very small, I mean 17 orders of magnitude small, it is much more accurate than this number. How do I know it's more accurate? We looked at more genes, right? The more genes you analyze, the more accurate you can be. That's all this is. Anyway, this review is going to be in Discord. I'll have somebody send it over to the other server.